In this section, we're going to look further at ways to evaluate limits, and it turns out that a lot of what we're going to talk about is really easy because often functions are continuous at the target point, and all it is a matter of taking f of the target point, and symbolically it goes like this. The limit as x approaches c of a function is just f of c. You see, if the function is continuous at that point. And for example, if we're taking the limit of this function, you see, of this expression, as x approaches 2, then take f of 2. Just replace the expression, in the expression, replace x with 2. We have 6 minus 5 or 1. So the limit then is 1. The limit as x approaches 4 of this means, what is f of 4? That is, put 4 in place of this x, and we have 4 and 4, 8. The cube root of 8 would be 2. The limit as x approaches 1 of the sign of this fraction looks kind of imposing, but it's no big deal. Replace x with 1, and we have the sign of pi over 2, which is 1. And for this one, these are even more trivial. The limit as x approaches 7 of x, you see, f of x is x, so replace x with 7, and we have 7. And even more fundamental than that would be the limit of a constant. The limit as x approaches 7 of a constant would be the constant. I mean, after all, if you look at the graph of this, it would be a horizontal line going through y equals 3. So as x approaches any value, the f of x is going to be 3. So these are rather trivial situations. Let's look at some others that are rather intuitive. Suppose we know that the limit as x approaches some target, the limit of our function as we approach the target is 7. Let's say that's given. We're not finding the limit, we're given the limit. Now, let's perform operations on this situation. The limit as x approaches c of 5 times f of x. 5 times f of x can be thought of as 5 times the limit of f of x. You see, the limit idea applies to the f of x. And so we just have 5 times 7. And that's what this is. That's all this is. This, the limit of f of x, you see, as x approaches c, is 7. So 5 times 7, 35. And the same goes with other operations. All we're doing is taking a real number and multiplying times f of x. But think about taking the square root of f of x. Well, the limit as x approaches c, you could think of this as, think of the square root out here as the square root of the limit of f of x. That limit of f of x is 7, so we get the square root of 7. And here we have the limit as x approaches c of f of x squared. Well, that's nothing more than, think of this bracket as being out here, you see, and all we would have is the limit of f of x, and all of that would be squared. So it's just 7 squared, or 49. Kind of an intuitive idea. Here's some more. Suppose the limit of f of x is 7, the limit of g of x is 4, and I'm not saying as x approaches c every single time. Let's make that assumption a little bit because it's very repetitive to have to say it all the time. But the limit of f of x is 7, the limit of g of x is 4. Now, what about the limit as x approaches c of f of x plus g of x? You see, doesn't it make sense that if the limit of that function is 7, the limit of that function is 4, that this is just 7 plus 4? Sure it is. And so we could think of it as, you know, we can kind of distribute this idea of limit through this bracket. So we'd say the limit of that function plus the limit of this function is what it's all about, so 7 plus 4, 11. And in a similar way, we could think of subtraction here of the two functions. We could think of multiplication of the two functions. If it was f of x times g of x, it would be 7 times 4. If it was f of x over g of x, it would be 7 divided by 4, 7 over 4, you see, for the result. Now, what about the composition? Well, that too is no big deal. The limit of f of g of x would be, now we're applying the limit idea to the g of x, and the limit of g of x, remember, was 4. So this is nothing but f of 4. And evaluate that, and we would find we would be resolving the situation. If it was g of f of x, we're taking the limit of g of f of x. We know that the limit of f of x is 7, so this is just g of 7, you see, and all of this is relatively intuitive. consider the limit of this rational function. And we know that often with rational functions we have undefined values. If x takes on the value of -1, then this fraction is undefined. Now, in situations like this, this turns out to be not a continuous function throughout the domain of the function. That is, for every x, we don't have a spot on the graph, and all those spots aren't connected. We sort of have a hole in the graph here. And, but the limit is still easy as long as the target point isn't the one that causes this rascal to be undefined. For example, if we're taking the limit of this as x approaches 0, hey, no problem. Our function is defined at that point. It's continuous in the neighborhood of that point. So all we do is find f of 0. Just replace these x's with 0 and we find the limit to be 1. In a similar way, the limit of the same function as x approaches 2, no big deal. Replace x with 2 in both places and we find 9 over 3 of 3. But what happens if we're trying to find the limit as x approaches -1? Now here's where we run into trouble. You see, it's not just categorically true that if we have a function that is not continuous somewhere that we're going to have trouble. We only have trouble if that point where it's not continuous turns out to be the target point. But it's not something that we can't deal with. There are several ways to deal with it. Now, we looked at a situation like this graphically earlier, and if you put the graph of this expression on your graphing calculator, you would be able to determine the limit very, very quickly and easily. We want to find an algebraic approach to it, and there are two fundamental techniques to deal with this situation. One of the techniques is just manipulation. And the technique here is factoring. So we're just factoring in the numerator. This is the sum of cubes. We factor into a binomial times trinomial, and oh happy day, the binomials here and here cancel. And when they cancel, we have x squared minus x plus 1. Now what we have fundamentally done here is we have transformed by this calculation and with this cancellation, we have changed our function, which is not continuous, into a continuous function. We are taking the limit of two functions that are equivalent except for that one point. You know, if you put both of these on the graphing calculator, they would overlap exactly except for the point that's undefined in this one. And so the limits as we approach that target point are exactly the same for these two. And so here we can just by direct substitution replace x with -1 and find that limit to be 3. Okay, so that's one technique, one situation. Here's the other situation. The other situation involves radicals. If, for example, we want the limit as x approaches 3 of this expression, notice if x is replaced with 3, we have an undefined situation here. When radicals are involved, jumpstart your thinking and the technique here of manipulation as being one of rationalization. Now, you've seen rationalizing before. You've heard the word before. It came up in situations like this where you have an answer like, 1 over the square root of 5 minus 2, let's say, in a problem. And you're kind of looking for an exact value. You don't want to leave the radical in the denominator. So you rationalize by multiplying by the conjugate of this denominator. The conjugate is the same binomial with a different sign. And so we're multiplying by the square root of 5 plus 2 over the square root of 5 plus 2. Does that jumpstart your thinking about this? And in multiplying, it's helpful with binomials to put parentheses all around to help with the multiplication process. And when the smoke clears on this, we'll not have a radical in the denominator, we'll have a radical in the numerator, and we say that's okay. All right, well, the technique is useful in clearing a radical from one part of a problem to another, from denominator to numerator, numerator to denominator. Here we're just using it as a manipulation technique. We're just trying to massage our expression, hoping that in the massaging process we're going to get a cancellation opportunity. And it turns out that we do here. We're going to rationalize the numerator. We're going to deliberately maybe create a fraction or a radical in the fraction and the denominator of the fraction, but we don't care about that. So what we're doing is this. We're saying, let's take this expression and multiply both numerator and denominator by the conjugate of the numerator. So we're multiplying by the square root of x plus 1 instead of minus plus 2. And we're going to do the same thing in the denominator. You see, we're just multiplying by a form of 1, which is what rationalizing is all about. We're not changing the value of the expression, we're changing its form. And that's what happens when we multiply by forms of 1. All right, so parenthesis will help us with the multiplication process all over the place in the numerator. In the numerator, let's see, we have the square root of x plus 1 times the square root of x plus 1. That's the square root of x plus 1 all squared, which gives us x plus 1. Then we know the middle term goes out because we're multiplying the sum of two numbers times the difference of the same two numbers, so we get the difference of squares. So we get minus the square of 2, which is 4. In the denominator, we're multiplying these two. Now I'm going to leave this in factored form. We could multiply this out, but I'm looking for a cancellation opportunity with this denominator because that's the troublesome part of the problem. So I'm going to leave this as x minus 3 times this other part. And now look at the numerator and think about a simplification. Sure, it turns out to be x minus 3. Oh, lucky for us. We get the cancellation as expected. And you know, with in algebra, you understood, and I hope you grabbed the idea that you should always be writing. That is, that you can see some ways to skip steps, but you need to resist the temptation of skipping steps. You need to, like, always be writing. If you're trying to think through and trying to skip steps, and you're thinking and not writing, then you're trying to skip too many steps. So here, let's see, we're canceling, and we have then the limit as x approaches 3 of this, which is all of this stuff. Now, by direct substitution, replace x with 3 in here, and we have, this becomes then (3 plus 1) or 4. The square root of 4 is 2. 2 plus 2, 4. This is 1/4. So that limit then turns out to be 1/4. Here's another situation involving some manipulation. The two classic situations, though, are the ones that we just had a look at. The first one had to do with factoring and canceling. The second one had to do with rationalizing a numerator. Other manipulations are just very straightforward. It's just a simplification of what we see in some way or another. Here's one example. The limit as delta x approaches 0 in this expression. Now, delta x, there's nothing mysterious about delta x. You may have seen the notation before. Don't worry about it. It's, I mean, it just is playing the role of any other variable, let's say, for our purposes right here. So we have delta x as a single entity. This is not delta times x, it's delta x. Okay? So as this amount approaches 0, what's going on over here? Well, our denominator is approaching 0, so we can't just deal with this by direct substitution. So we take the approach that we're going to manipulate a little bit. And to manipulate, we're expanding what we see, performing indicated operations, and just looking for opportunities to cancel. So 2 times x plus delta x is 2x plus 2 delta x. And we bring down the minus 2x. 2x minus 2x go out, so we have 2 delta x over delta x. The delta x's cancel, and we have a constant then. So we're looking for the limit as delta x approaches 0 of the constant 2. That is simply 2. Here's another manipulation situation, kind of similar, but but different in that we're using function notation. Here, f of x is defined to be 3x plus 2. And we want to find the limit as h approaches 0 of this. You might recognize this as a difference quotient. And it just uses function notation, and we're manipulating with function notation. That's all there is to this problem. F of x plus h means in the f function, replace x with x plus h. So in this expression, replace that x with x plus h. So we would have 3 times x plus h plus 2. That's here. And then what does this mean? It means f of x. Well, this is f of x, so it's minus that expression. Now notice the introduction of the parenthesis to make sure we don't get confused with the sign changes here. And incidentally, let's back up a little bit. The need for the manipulation was that our target is approaching, our target point, 0, is causing the denominator to become 0. And that's the reason for us going through all of this process. All right, at any rate, let's see. 3 times x plus h, 3x plus 3h, bring down the 2. Minus 3x minus 2, then 3x minus 3x go out, 2 minus 2 go out, and again we have a nice happy situation with 3h over h. The h's cancel, so we have the limit of a constant, which gives us the constant 3. For the trig functions, we establish or calculate limits by direct substitution. That is, the limit as x approaches c of sine x would be simply sine c. So it's f of c, you see, for that sine function. And the same way for cosine x. If we want the limit as x approaches c, we just find cosine of c. For tangent, same idea, and for the other 3 as well, cotangent, secant, and cosecant. Now, just as an example, if we want the limit as x approaches pi over 2 of sine x, we find sine pi over 2, which is 1. If we're thinking about the limit as x approaches pi of x cosine x, just replace the x's with pi. You can separate the idea here. You separate the thinking into this is x times cosine x. So we can, instead of the limit of a product, we can think of the product of limits. You see, we can think of the limit of this factor times the limit of that factor. Sometimes that idea, that conscious separation as to the product of 2 separate limits is kind of helpful in the manipulation process later. That's why I write it in here. You don't always have to write this. You know, this is such a trivial situation that you can go directly to that step. But I want to show this because in the future we'll have occasion where we need to write that step. At any rate, so we're making the substitution here, and so we have pi times cosine pi. Cosine pi is -1, so negative pi would be the limit. Now, I said all of that, and all of that is trivial and kind of intuitive, but we come to the point where there are some special situations. There are 2 special trig limits. And I want you to write this down somewhere. It's important to have these as reference. Kind of like having identities as reference when you study trigonometry. So these are our reference ideas. Special trig limits. The first is the limit as x approaches 0 of sine x over x turns out to be 1. And the limit as x approaches 0 of 1 minus cosine x over x is 0. So those are very important to kind of commit to memory or have as reference as you're going through your assignments. And notice that, that these are kind of special. We can't calculate these by direct substitution because a substitution would give us undefined situations, because when these x's are replaced with zeros, we have undefined fractions. So these have to be proven in some way, and incidentally the proof of this is in your textbook if you'd like to look at it. It would be worthwhile. A theorem called the squeeze theorem is used to prove these. And we'll talk about the squeeze theorem just a little bit, but it's useful in the proof of these rascals. Now, using these is a matter of putting problems into the form that we see here. Now notice sine x over x. It's the correlation of these two, you see, that makes this turn out. This could be the sine of, 5x over 5x, or the sine of the square root of something over the square root of the same something. Would follow this pattern, and in a similar way here. Okay, let's look at a couple of problems. If we have the limit as x approaches 0 of tangent x over x, well, we'd like to put this, it kind of looks like it's in the form of the sine x over x, so we would like to manipulate this so that we see sine of something over the same something, you see, so we can apply this special limit idea. So we think of tangent as sine over cosine, so sine x over cosine x, and we're just in the manipulation mode here. We're just massaging the fraction to put it into a particular form. We've done it so many times before with identity, so this is not any really big deal. So we have this divided by x, or times 1 over x, and the x now is a factor in the denominator. We can separate those out. We can change these around. You know, there's all kinds of ways to manipulate it, but the way we want to manipulate it is to think of sine x over x, and the cosine x in this denominator as a separate factor. So we have 1 over cosine x times what we're looking for. You see, this is the form that we were looking for. Now apply the limit to both of these factors. And so it's the limit of that factor times the limit of this factor. And now cosine 0, remember, is 1. So this is 1 over 1, or 1. And this, because it's one of our special trig limits, is 1. 1 times 1, 1 for the result. Here's another one. We have the limit as x approaches 0 is sine 3x over x. Now, this is not in the form where we can just say this is 1. We have to perform some manipulation here. So we'll multiply. We're deciding, well, how can we make this item look like that item? How can we make these look alike? Well, we can introduce a 3 factor in the denominator, but if we introduce that factor into the denominator, we have to introduce it into the numerator. We're multiplying by forms of 1, so we multiply by the form 3 over 3. And now 3 is a factor in the numerator, so it's 3 sine 3x. In the denominator, 3 times x, 3x. Great. We separate the 3 from the sine 3x. You see, we think of the problem as 3 times the form that we're looking for, and now apply limit to each of the factors separately, the limit of the constant, and then the limit of this form. The limit of the constant is the constant, and the limit of the form, you see, which we had over here, is 1. So 3 times 1, 3 for the limit of that expression. I mentioned earlier that a theorem called the squeeze theorem is useful in proving our special trigonometric limits. And let's talk about the squeeze theorem just a minute. It goes like this, that if we have a few functions whose behavior is like this, that h of x is less than or equal to f of x, and f of x is less than or equal to g of x for all x values in the domain of these functions, and if the limit as x approaches some target of the h function is L, and also the limit as x approaches the same target of the g function is L. You see, we're approaching the same target, and the limit for that function is the same as the limit for this function, then that limit must be the same for the function that's squeezed in the middle. So the limit as x approaches c of f of x has got to be L. Graphically, it looks like this. It's kind of intriguing, and it also gives a little more validity to the idea of the name the squeeze theorem. We're squeezing f between g and h. Here, g is above, clearly above or greater than or equal to f, and f is greater than or equal to h. I should say it in the same way it's said over here. H is clearly less than or equal to f. F is clearly less than or equal to g for all x in the domain of the functions. Now, notice that here's our target point. If we're thinking of this as our c value, then as x approaches c, the limit as x approaches c for the h function is that value. The limit for g is also this value, and this value, by this value I mean this L, vertical distance, you see. Then it must be the case that the limit as x approaches c for f of x is also the same L. Comes in handy in situations where the limit of some target point for the f function is difficult to calculate. So we calculate limits that are easier for functions that allow us to squeeze f in between them. Situation like this. Now, I'm not defining the f function at all, but we can use the squeeze theorem to find the limit as x approaches, let's say, 0 of f of x in this situation. We have 4 minus the absolute value of x over here. We have 4 plus the absolute value of x over here. And to calculate the limit as x approaches 0 for f of x, even though we don't even have an f of x, is relatively easy because we have a function here, we have a function over there. By substitution, as x approaches 0, this becomes 4. And as x approaches 0, this becomes 4. So it must be the case that f of x also has a limit of 4. You see, it is squeezed between those two. Now, it's important that these two have exactly the same limit. That's a very important idea in the squeeze theorem. If these are different from one another, then we can't make any conclusions about a limit involving f of x. But if these are the same, then the limit for f of x has to be that same number. Let me say a word or two about assignments. I've noticed in the textbook, and you will notice, maybe you already have noticed, that there are a lot of problems at the end of the problem, or at the end of the sections. And as you know, we talk about manipulative skill here. We talk about manipulation and finding things like limit and so forth, and techniques, and those techniques are practiced in the assignment. And after those practice problems comes problems that are a little bit of a reach, maybe. Proofs, for example. Prove this, think about that, describe this. You know, those kinds of problems involve what have you found out? What do you know now about all of this practice that you have done? Now, when you come to those kinds of problems in the problem set, don't be discouraged if you can't work every one of them immediately. The answers to those problems are not going to be trivial. And if you have trouble with them, don't worry too much about it. Think about it some. Try to think through. That exercise, the exercise of thinking through, is going to help you understand conceptually what we're talking about all over the place. And the more you think about it, the better you're going to be at understanding what is going on. But if you bump into a brick wall, don't feel bad about that. Everybody does that. These are not easy problems. But what you want to do is eventually get to the solution and understand what the solution is. Look in the back of the book or look in the solutions guide. But find the solution, ask some questions about it if you're working with some other people, and develop an understanding, even if you aren't able to develop that understanding on your own. Anyway, I just wanted to give you a flavor for that, because some people, when they bump into problems like that and they're unable to accomplish them, they think badly about themselves, and they think, well, gee, maybe I'm not really catching on to this. Well, that's not really true. You catch on through either misunderstandings or not finding the right thing in a rather trivial or straightforward way. You have to think through it. You got to struggle with it a little bit to really develop a good understanding. And don't worry about that struggle. That's part of the process, and it's normal operating procedure in calculus.